Welcome to my Atari 7800 basic tutorial. So get your Atari mug and fill it with your favorite beverage. Put on your spectacles if you got 'em, and let's make a thing! Hello, Internet people. Welcome to Lesson 2 of our Atari 7800 Basic tutorial. Today we're going to learn all about sprites. On our first lesson in Atari 7800 Basic, we made a simple Hello World program with a color rotating background. In this lesson, we'll begin to turn that idea into a game. The game we're making is called UAP, which is the modern name for a UFO and stands for Unidentified Aerial Phenomena. This game is based on a certain Discovery Channel TV show. In the game, you play a UAP, but that's all we know so far. So in this lesson, we will design a player sprite and get it moving on the screen with a joystick. If you were like me, you found out about the Atari 7800 sometime in the summer of 1984, possibly reading a magazine like Electronic Games. The most exciting thing about the Atari 7800 was its sprite capabilities. Back then, the capabilities of most video game systems were defined by how many objects they could move around the screen. The Atari 2600 with the TIA chip had 5 sprites: Player 1, Player 2, Missile 1, Missile 2, and the ball. The Atari 5200 and the Atari 400 and 800 with their CTIA and GTIA chips had 5 hardware sprites, but also a complicated display list and character set redefinition system that made it seem like many, many more. But the Atari 7800 with its Maria chip offered something completely different. According to Electronic Games, it would put nearly 100 sprites on the screen at the same time, and it would make a game like Robotron, then and still now one of the most impressive arcade games ever made, possible on the Atari 7800 with very few compromises. But then the Atari 7800 wide release was canceled in 1984, and by the time it came out almost 3 years later, the Nintendo Entertainment System had conquered America. When I finally did get to play the 7800 version of Robotron sometime in 1987, I was not disappointed, as it was spectacular. There were so many independently moving objects on the screen with no flicker. It felt like the culmination of everything we wished for in 1984. But it was too little too late by 1987. I could only imagine what games the 7800 could have had by that year if game developers were 3 years into the development cycle. So to me, this is the actual lure of the Atari 7800. It's what could have been. And much of that stems from the sprite capabilities of the Maria graphics chip. One other note. Atari 7800 Basic is very powerful, but it's still a game engine built in assembly language that abstracts the full power of the Atari 7800. In this regard, it's powerful, but still limited compared to programming in full assembly language. A good indication of this is how Atari 7800 Basic handles zones. Recall, zones are horizontal bands, 8 or 16 pixels high. Only a certain number of sprites, determined by how long it takes to draw each line on the CRT, can be displayed at a time in a zone. But Atari 7800 Basic abstracts the programmer from having to deal with the zones. It says this: the Maria splits the screen into a series of horizontal bands called zones. A 7800 game typically spends a good deal of time setting up memory structures for Maria called display lists. Display lists tell Maria which characters and sprites should be displayed in any one zone. 7800 Basic will deal with zones and create and manipulate display lists on your behalf, so there won't be any further mention of them in this guide. This is probably a good thing to get started, But as you advance, you may find that you need more flexibility, and that flexibility will come by programming in assembly language. But that is a little much for these tutorials. We're going to concentrate on what Atari 7800 Basic can do for us. Note: in the last lesson, I may have failed to make a few things abundantly clear. These are rules to live by when programming games in Atari 7800 Basic. I call them the 3 C's: code, case, and configuration. Well, okay, I just made that up on the spot, but you'll see what I mean. Code. Remember that tabs matter in Atari 7800 Basic. All regular code must be tabbed in at least one space, or it will cause errors. All labels for go-tos and go-subs must be in the first column, so not tabbed in one space. There are a few exceptions to this, but we will talk about those if we get to them. Case. Case matters. If the code example says 32K with a lowercase k, and you use an uppercase K, the compiler will throw an error. Just this one concept can save you a lot of headaches. And finally, configuration. VS Code needs to be configured to compile your code using the Atari 7800 compiler that came with Atari Dev Studio. This usually occurs automatically if you have saved your source with the file extension .78b. However, if that does not occur, you need to configure VS Code to compile your 7800 binary. Check the lower right of VS Code. If it says 7800 Basic, white text on blue, you are good to go. If not, click on the text in that location. It might say something like Be Atari Basic, then select Atari 7800 Basic on the selection screen. By remembering the 3 C's, code, case, configuration, you should avoid a lot of headaches when compiling. Now, on to the lesson. Step 1. Title screen game loop. Okay, the first thing we need to do is separate our title screen from our game loop so we can have a place to initialize the game and a place to execute the game. We'll be working from the code designed in Lesson 1, Hello World. The first thing we do is add a couple more variables, lives and score. We're not actually sure what we're going to use these for yet, but they are indicative of the types of variables our game will use. First we define them, then we initialize them like this. Dim lives equals var3, dim score equals var4, lives equals 0, score equals 0. Next, we will change the name of game loop to title loop and make sure our goto now targets the correct label. So instead of goto game loop, we'll say goto title loop. Let's talk a bit about labels because I believe we glossed over that topic in Lesson 1. These are jump labels and can be used with either goto or gosub. My convention is to start them with an underscore so I can easily tell them when I see them. Labels must be in the first column of a line. Most other code must be one space in, or the compiler will barf until it has no idea what to do. Some people experience this with Lesson 1, and I'm truly sorry I did not specify better that most of the code had to be tabbed in one space. Next, we'll change the name of the title screen from Hello World to UAP. Notice we only use lowercase letters. That is because only lowercase letters were defined in our font graphic that we introduced in Lesson 1. If you want lower and uppercase letters, you can draw your own font graphic. In fact, in 320 mode with double wide fonts, you can get pretty elaborate with the design of your font. If you create a text-heavy game for the 7800, you may want to explore those modes and options. Next, we plot the new UAP text we changed from Hello World. Then we'll introduce the joystick. Then we'll test the first and second joystick buttons of the first joystick, Joy 0, Fire 0, and Joy 0, Fire 1. And if either is pressed, we'll jump to a new label that we create called underscore initGame. In initGame, we will reset everything. This is redundant now, but as the game gets more complex, there will be certain variables we want to initialize before the game executes and ones we want to reset every time the game starts. And now we create a new function named underscore game loop. It'll look pretty much like the old title loop that we changed to game loop, except we draw some placeholder text that says game to remind us that we are no longer on the title screen and that the game is about to start. Enter as plot cares game 0,68,5. When we recompile the code, it will look like this. The title screen will still rotate colors, but it says UAP. By pressing Fire 0 or 1, the title screen will disappear and we'll see the game placeholder text. Now, I edited this video to make it look like I got all of this right the first time, but that's not the case at all. In fact, the first time I compiled, I got an error. So I'll show you what that looks like. The compiler will stop and give you information to help you figure out what's wrong. The most useful information for beginners is this list of unrecognized symbols. Ignore the ones that you did not define and look for things you might have messed up. For this step, I forgot that the name of our loop was game loop, not game title. Another common error with labels is not left justifying them. Again, most other code needs to be at least one character tabbed in, but labels need to be in the first column. So if I go ahead and fix the code and rerun, everything executes as expected. Step 2. Now we're going to get into it. Drawing sprites. So I've been clicking on this menu bar at the bottom of the screen and not talking about it at all. This little bar was added by Atari Dev Studio. Most plugins for VS Code add a little toolbar like this. The functions are welcome, takes you to the Atari Dev Studio plugin page, sprite editor, it is what it says it is, sprite editor, compile, and compile and run. We will spend most of our time on sprite editor and compile and run. To create a player sprite for the game, we will click on the sprite editor button. You will see a screen that looks like this. Now we create a new sprite that is 16 by 16 with 4 colors for mode 160A and TSE. The windows can be arranged to make it easier to see everything. You can grab them and move them around, resize them, etc. I usually resize so I can see an entire sprite and also the current set of sprites in the sprite file I'm making. Next, we set our colors. For the sprite, I'd like white, gray, and red. Recall that 160A mode has more pixels, 192 in the Y direction, and less in the X, which is 160. So we need to accommodate that when we draw. A sprite file with a .spe extension can hold as many sprite definitions as is reasonable to work with. .sp files are not sprites though. Each sprite must also be exported as a .png to be used in the game. When I'm done designing the first UAP sprite, I want to make it animated by inserting a few little details that can move when we add more frames. I press the copy sprite and then edit the next sprite to make it animate. I do this 2 more times so my UAP sprite, the player, as you play the UAP in the game, will have 4 frames. Next, I save the player_sprite.spe file in a directory of my project named images. I call it player.spe. Then I export each individual frame as a PNG file, naming them player1 through player4.png. Now we are ready to load the sprite into our Atari 7800 game and display it. Now we will display these 4 sprite frames in succession to make it look like our UAP is animating. The first thing we need to do is create a color palette to match the colors we used in our sprite. We can find the colors we need to set in 7800 BASIC by looking back in the sprite editor and rolling over each color to find its hexadecimal value. In this case, the values are 0D, 08, and 33, which are 2 shades of gray plus a deep red. Next, we will include the sprite images we created. The order of the inclusion is very important. The order of these sprites is used for animating them. You can easily animate sprites that are loaded in succession. In graphic, images /player1.png 160A 0, 1, 2, and 3. The images of the directory we saved the player sprites in, and the 0, 1, 2, 3 are the colors in the palette, and we will get to that. The file names of sprites we will use directly in the code to identify them. They can't contain any special characters and need to start with a letter. After the name, you have additional parameters. 160A is the graphics mode of the sprite. If you don't specify, 7800 BASIC will default to 160A, which are 3 color sprites. However, in the next lesson, we'll see how we can load 12 color sprites in the same way by specifying 160B. The other numbers are color indexes. These can be very confusing, but we'll have an example in just a bit that shows how to use them. Next, we will create a couple variables to hold the X and Y location of the sprite. Dim player X equals var5, dim player Y equals var6, and initialize them to 0. Player Y equals 0, player X equals 0. In the init game subroutine, we'll then initialize the BIOS for the start of the game. Player X equals 70, player Y equals 90. This is a good time to explain variables a little bit in depth. In the first tutorial, we told you that Atari 7800 Basic has 126 built-in variables, var 0 through 99, and A to Z. Some functions in 7800 Basic require the A to Z variables, so I avoid using them. You can also assign direct memory locations to another 1,535 single-byte variables, which is ample space for most simple games. Each variable in Atari 7800 Basic represents a single byte, which of course can hold numbers 0 through 255. Luckily for us, in 160A mode, the screen size is 160 by 192, which means a single byte can hold the X position and a single byte can hold the Y position for any sprite. Now let's draw the sprite in our game loop using plot sprite. Game loop, clear screen, plot sprite, player 1, player X, player Y, draw screen. Then go to game loop. The plot sprite command has 5 parameters. Name of the sprite, palette number, of course this is 1, 0 was for our original text, we're using 1, X location, Y location, and animation frame. Optional, we don't have it here, but we will use it soon. When we compile and test the code, our UAP sits pretty much in the center of the screen. Okay, this is where things get a bit technical. Now let's look at the compiler output to understand a little better what we have done. With the font and 4-player sprites we have loaded, we have used about 1K in ROM space. For a game with zone height of 16, the graphic block size are 4K in size. Blocks are created automatically. We have used just about 1K of ROM space. Graphics in different blocks will not easily animate. So as you create more and more graphics to load into your game, you might need to manage the order of how things are loaded. Also, the more graphics you have, the more chances you will need to use bank switching. One more interesting thing to see here. The second to last line says $1830 to $FFF used as zone memory, allowing for 31 display objects per zone. With a height of 192 pixels and a zone height of 16, that means we have 12 zones. 31 display objects per zone equals 372, so conceivably we could get 372 sprites on the screen. This is why people were so excited about the Maria chip in 1984. However, even though a zone has the memory for 31 objects, that doesn't mean they can be displayed in the time it takes to draw each scan line. Also, those display objects are everything, including text and the background map, etc. Don't worry though, there are ways to expand this using extra RAM in the cart and using double buffering, which will help make sure everything that needs to draw gets displayed. Step 4, animating the sprite. To animate the sprite, we need a way to remember which player frame we are displaying. I like to use very descriptive variables. So we will call this variable player anim frame. So dim player anim frame equals var 7. We will initialize this before our game starts, player anim frame equals 0. Well, also after our init game label, player anim frame equals 0. Then in our game loop, we'll add the player anim frame variable as the last optional parameter to plot sprite. Recall that there was an optional parameter for frame. After that, we increment the player anim frame, then test to see if it was more than 3. More than 3 because everything starts at 0, so for more than 3 we'll be above 4, which means we want to reset back to 0. If so, we do reset it back to 0. Notice a couple things here. We only ever have to use the name of the first sprite, player 1. So plot sprite player 1, 1 being the palette, player X, player Y, and then player anim frame. But we only plot player 1. Because we loaded all 4 sprites in sequence, it will treat the subsequent sprites as a frame of this first sprite if we use the optional frame parameter as we did here. There is no magic here. The frame parameter is simply moving to the next 168 4-color sprite. This could be anything. For instance, if you have an explosion that is loaded directly after the player sprite and you don't reset the player anim frame back to 0 when it reaches 3, your explosion frames will be displayed as frames of your player sprite. Now let's test this. When you press the rocket and compile this version, you'll see the UAP animating very quickly in the middle of the screen. It's neat, but too fast. There are many ways to slow this down, but we'll employ one that will be necessary for our game: double buffering. Double buffering allows you to define how many frames it will take to draw the screen. It also regulates the frame using a timing delta calculation so animation is smoother. This is a function of Atari 7800 Basic provided to help manage sprites zones in memory and is very useful. In our boilerplate at the top of the program, we will use the double buffer directive to turn on this functionality. Double buffer on. Then in our underscore game loop, we will replace draw screen with this line of code. Double buffer flip to. Flip to tells Atari 7800 BASIC to use 2 frames to draw the screen. When we compile and run this version, you will see the UAP animates slower at 30 FPS or 30 Hz and not at the default 60 FPS or 60 Hz. Let's look at the compiler output. Now the compiler tells us we only get 14 objects per zone. This is because double buffering is turned on. The resources needed to smooth out the animation mean there is less memory for sprites. This is fine, but don't worry. We were never getting 300 plus sprites on the screen anyway. There are other levers we can pull to get more sprites in a zone that we will learn about later. But we are now getting closer to a more realistic number of sprites that can be displayed. While we will ultimately need double buffering for this game, it's not a great way to control the speed of animation. Most likely, we'll want to control each sprite's animation individually. To do this, we will create a new variable named playerAnimWait. We'll use this variable to count frames before we move to the next animation frame. Dim playerAnimWait equals var8. We will also initialize it like the other variables before the game starts running and after the init game label. PlayerAnimWait equals 0, and in init game, playerAnimWait equals 0. Now, in game loop, instead of incrementing playerAnimFrame every time the subroutine loops, we will count to 3 by incrementing playerAnimWait. Every time it gets above 2, we will then increment playerAnimFrame. By doing this, we will get much more control over the speed of the animation. PlayerAnimWait equals playerAnimWait plus 1. If playerAnimWait is greater than 2, then playerAnimFrame equals playerAnimFrame plus 1, playerAnimWait equals 0. If playerAnimFrame is greater than 3, then playerAnimFrame equals 0. Double buffer flip to go to game loop. When you compile and run this time, you will see the sprite animated slower, but also that the middle portion doesn't look right. Now that we actually can see the sprite, we can also see how it animates. Let's go back in the sprite editor and update the frames to make a different animation. Instead of animating horizontally, let's make the middle portion animate vertically. Now save player.spe when we are done and export each frame again. When we compile and run the code again, something odd happens. It looks like a couple of the colors are different than what we defined in the sprite editor. This happens a lot. There's an explanation for it about how the different indices get transposed depending on which color is used first or something, but I've never quite understood it. What it means in practical terms is that you can't always trust the colors as they are saved in the .png, and you might have to reorder the indexes. The good news is there's an easy way to fix this, but it might take a bit of trial and error. Remember those final parameters in the ink graphic command, 0, 1, 2, 3? These are Maria color indexes. To fix this little color glitch, all we need to do is swap the second and third indexes when we load the sprites. Now when we compile and run, the colors look correct and the animation looks smooth. By the way, Atari 7800 BASIC has some recent functionality that allows the programmer to extract color values directly from loaded .png sprites and put them into color constants. I have not used this functionality yet myself, but it looks very interesting. Step 5, move the sprite. Let's finish up this lesson by allowing the player to move the UAP around the screen using joystick 0. Honestly, this is the easiest lesson yet. All we need to do is stick this very much self-explanatory code in the game loop. If joy 0 left, then player X equals player X minus 1. If it senses that the joystick is moving left, move 1 pixel to the left. If it's right, move 1 pixel to the right. If it's up, move 1 pixel up. If it's down, move 1 pixel down. We'll move the UAP up 1 pixel depending on which direction of joy 0 is pressed. This code is in no way optimized. We should probably add a control wait counter as well, or we'll read the joystick or fire button 30 times a second, which might be too many. But for now, let's compile this code and start moving. Well, that's it for lesson 2. Be sure to read the notes and download the code from GitHub. Good luck, and let's get some great new games on the Atari 7800, history's most underutilized game console. Until next time, into the vertical.